Welcome back to the deep dive. We spend so much of our time talking about the amazing things technology does. The AI models, these incredible graphics engines, massive data sets.
Mhm.
But today, we're doing something a lot more foundational. We are stripping away all those complex software layers, all the graphics, and getting right down to the fundamental language that powers every single digital device you own.
Exactly. We got this fantastic stack of sources from a listener, all
Yeah.
focused on the absolute core of computation numbers. But I mean, not the numbers we learned in grade school.
Right.
We're talking about how those abstract concepts are managed by machines that are, at their heart, just billions of tiny switches that only know two things,
Yeah.
on or off.
And that's really the core paradox we're tackling today, isn't it? Our whole mission for this deep dive is to get into that reality. Computers don't inherently process the number 3 or 100 or pi. They just process patterns of bits.
And if you really want to understand technology, I mean, truly understand it, not just use it, maybe you want to debug it or just appreciate it, you have to grasp how we, the humans, take those, chaotic-looking patterns of zeros and ones and impose meaning onto them.
It's like learning the alphabet of digital reality.
It really is. It's the fundamental syntax.
And it's deceptively simple on the surface, but the consequences of getting that interpretation just slightly wrong, they can be catastrophic. So we've structured this deep dive to build up layer by layer, starting with the most basic concept, binary. That's the machine's native tongue.
From there, we'll move to the essential translation layer, hexadecimal, which is basically the shortcut we invented to save our own sanity from reading long binary code.
And then we get into the really tricky part, the real complexity. How computers deal with polarity using signed versus unsigned values. This is a context where, and this is amazing, the number 245 can suddenly become -1. And finally, we'll look at the surprising and frankly unavoidable compromises we make when we try to represent decimals using floating point math.
And we're really going to spend time on the mechanics of this. We're going to see how the exact same string of bits can carry multiple, completely contradictory meanings. It all depends on how the programmer defined that specific variable.
This isn't just theory.
Not at all. This is where some of the biggest, most subtle, and most dangerous software bugs come from.
All right, so let's start at, well, not base 0, but base 2 in this case. In our everyday life, we are just so comfortable with base 10, the decimal system.
Of course.
We've got our 10 wonderful digits, 0 through 9. It feels universal.
It feels universal because we're primates with 10 fingers. It's a total evolutionary convenience, not some kind of mathematical necessity. A computer, though, which is based on these silicon transistors, it doesn't have 10 states. It has one switch with only two states,
Charged or discharged.
on or off. High voltage, low voltage, whatever you want to call it. Two states.
So those two electrical states give us our two digits, 0 and 1. And that's it. That is the absolute non-negotiable foundation of all digital information, base 2 or binary.
And, when people first approach binary, they often get intimidated. They see these massive, long strings of ones and zeros, and they just assume it must be some completely alien mathematical concept.
Yeah, it looks like something out of the Matrix.
Right. But the foundational principle, and our sources really emphasize this, is that it works on the exact same structure as our comfortable base 10 system. It's all about positional notation.
Which just means that the value of any digit depends entirely on where it sits in the string. Let's make sure we walk through that example slowly because it's so key.
It really is. Positional notation is the key that unlocks absolutely everything here. When we write a decimal number, let's say 347, we aren't just jamming three symbols together. There's an implied, structured, base 10 breakdown happening.
Right, so if you look at 347, the 7 is in the ones place, which is 10 to the power of 0. The 4 is in the tens place, 10 to the power of 1. And the 3 is in the hundreds place, 10 to the power of 2.
Exactly. So 3 times 100 plus 4 times 10 plus 7 times 1. That gets you 347. It's beautifully consistent, all built around powers of 10. Binary just takes that exact same brilliant structure and swaps in powers of 2.
And this is where the efficiency for the machine comes in, right? Because the hardware only has to manage those two states, 0 or 1. The arithmetic for the silicon becomes incredibly simple. But for us humans, the weights of those positions change dramatically.
Well, they absolutely do.
Yeah.
Instead of weights of 1, 10, 100, 1,000, you get weights of 1, 2, 4, 8, 16, 32, 64, 128, and so on.
Every position moving from right to left just doubles the potential value.
Yep.
So let's decode a specific binary number that came up a lot in our sources. 10, 11. We read it the same way we do with decimal numbers, right? starting from the rightmost digit, the least significant bit.
That's right. So we need to assign those powers of 2 to the positions, starting with 2 to the power of 0. The rightmost digit is a 1, and it's in the 1 place, the 2 to the 0 position. So we count that.
Okay, so that's a value of 1.
The next digit over is also a 1. That's the 2's place, 2 to the power of 1. So we add 2. So far we have 1 plus 2, which is 3.
Got it. The next one is a 0. That's the 4's place, 2 squared. Since it's a 0, we just ignore it.
We ignore it completely.
Yeah.
Then the leftmost digit is a 1, and that's in the 8's place, or 2 to the 3rd power. So we add 8.
So we sum up the weights where the bit is a 1. We have 8 plus 0 plus 2 plus 1. That totals 11.
And there you have it. The binary number 1011 is just another way of writing the decimal number 11. It's just addition, but you're only ever adding powers of 2.
What's really fascinating, and it speaks to the speed of modern computers, is how quickly these numbers grow. In base 10, to represent a number like 1,000, you need 4 digits.
But in binary, to get to about 1,000, specifically 1024, you actually need 10 digits. It's 2 to the power of 10. Now that sounds less efficient.
It sounds much longer.
It is longer to write, but because the underlying hardware is so dead simple, just on-off switches, the raw computational speed more than makes up for the longer representation.
And this naturally leads us to the fundamental unit of digital storage that everyone's heard of, the byte. For decades, the standard grouping has been 8 of these bits.
Yes. And if you have 8 bits, that 1 byte, you can represent 2 to the power of 8 different combinations. That's 256 unique values. And that range, 0 to 255, that is the absolute non-negotiable limit for that single block of data.
So for anyone listening who wants to get a feel for decoding binary on the fly, just memorizing those first 8 positional weights is the essential shortcut.
Absolutely. 1, 2, 4, 8, 1632, 64, 128. If you see a 1 in that position, you turn that weight on and you add it to your sum.
And that's the whole mechanism.
That's it. And the key takeaway here is, well, it's profoundly simple, but so easy to forget. The computer never sees 11 or 255. It only registers the pattern of electrical states, 1011 or 1111. The integer value, the number itself, is purely our human-imposed interpretation that we apply to the electrical state of those 8 little switches.
We're forcing a concept onto a physical reality.
That's a perfect way to put it.
And that forcing of a concept is the crucial first step.
Yeah.
But it immediately introduces a very practical problem. Those binary strings get long, very long. If 8 bits only gets us to 255, just imagine the length of a binary string for a common 32-bit or 64-bit integer. The numbers are just staggering.
I mean, if you're dealing with 64 bits, you're literally looking at a string of 64 ones and zeros. No human being can read that efficiently or without making mistakes. And that brings us to the human shortcut that became, well, absolutely mandatory.
We had to move from the machine's native language to a human-readable shorthand. This is where engineering really meets psychology. Binary is perfectly efficient for the machine. But if you're a programmer or an engineer and you're looking at a memory dump or trying to understand a raw data packet coming across a network, reading strings of 64, 128 ones and zeros is not just painful, it's incredibly error-prone. You miscount a single 0 somewhere in the middle, and the entire system could crash.
It's just visual overload. Our brains are not designed to parse these massive, undifferentiated sequences of just 2 symbols. We need chunking. We need a way to condense that information efficiently. And that necessity led directly to hexadecimal, or hex. It operates on base 16.
Right, base 16. This is where we start getting a little creative with our symbols. We need 16 unique characters to represent the digits from 0 all the way up to 15.
So we use our familiar digits, 0 through 9, and then for 10, 11, 12, 13, 14, and 15, we just introduce the letters A, D, C, D, E, and F.
That transition from 9 to A, where A represents the value 10, is essential, and F represents 15.
Yep. So a hex number, like, say, 1F, just means 1 times 16 to the power of 1 plus 15 times 16 to the power of 0. So that's 16 plus 15, which is 31 in decimal. It's the same positional notation principle, just with a much bigger base.
But the real genius of hex, the reason it became the standard human shortcut, isn't just that it's base 16, it's its perfectly calibrated relationship to base 2. What's that fundamental, beautiful alignment between binary and hex?
The alignment is just mathematical perfection. One single hex digit represents exactly 4 bits.
Exactly 4.
Think about it. 4 bits, 4 positions. They can count from 00000, which is decimal 0, all the way up to 1111, which is decimal 15. Since base 16 needs digits up to 15, one single hex symbol is the perfect compact fit for 4 binary bits.
It's a perfect lossless translation block. You don't lose any information, you don't waste any space, it just maps one to one.
And because of that ideal 4-bit chunking, it means that 2 hex digits perfectly represent a full byte, which is 8 bits. That is the massive critical efficiency gain that makes hex absolutely indispensable in any kind of low-level engineering.
You're reducing the character count by a factor of 4.
Instantly.
Let's use that really compelling example from the source material to hammer this home. Let's take the binary string, 1 and 11, 11, 11, 11. That's 8 ones in a row. It's the maximum value you can hold in a standard 8-bit byte.
Okay, so if you were forced to read that binary string, you'd have to calculate it out. 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. And if you do all that math correctly, you get the decimal value 255.
And it takes time, and you could easily make a calculation error.
Yeah.
Now, if we applied the hex shortcut, we just chunk that byte into 2 groups of 4 bits. The first 4 are 1111, and the second 4 are also 1111.
And since 1111 is the largest value you can represent in 4 bits, it's decimal 15, it translates directly to the hex digit F.
So 1111 becomes F.
And the other 1111 also becomes F. Therefore, that long binary string, 11, 11, 11, 11, simplifies right down to the far more readable, far more compact hex FF. We just compressed 8 characters down into 2.
And the mental effort to parse FF is almost 0 compared to parsing 11111111. It's the exact same information, just formatted for human efficiency. And if you imagine that applied to a 32-bit integer, you go from 32 ones and zeros down to just 8 hex characters.
It's a total game changer for debugging. It's exactly why hex is called a human shortcut. It just massively reduces the visual and cognitive clutter. And this isn't just some abstract knowledge. You see this system in constant use in crucial everyday applications, many of which, you're probably already encountering.
Okay, so where are we already doing base 16 math without even realizing it?
Well, the most common visible application is probably in web design and digital graphics. If you've ever picked a color using an RGB hex code, you've seen something that looks like hashtag FAA00. That hashtag is a signal for hexadecimal notation.
I've always wondered what those pairs of letters and numbers meant.
It's quite simple, really. FF is the first byte, and it defines the red intensity. AA is the second byte for green intensity. And 00 is the third byte for blue intensity.
And since each pair 2 hex digits represents 1 byte, they can range from 0 to 255.
Exactly. So 00 is minimum intensity, and FF is 255, maximum intensity. So hashtag FAA00 means maximum red, high amount of green, and absolutely no blue, which gives you a very rich orange color.
That makes perfect sense. It's a language of intensity, just encoded efficiently.
And beyond graphics, hex is fundamental in anything related to memory management and debugging. When a computer program crashes, it often gives you a core dump, basically a snapshot of the program's memory at the exact moment of failure. The most crucial information in that dump is the memory addresses.
And memory addresses, especially on modern systems, can be absolutely massive 64-bit numbers. Writing that in binary or decimal would be ridiculous.
Precisely. In decimal, a 64-bit address would be 18 or 19 digits long. In hex, it's a much more manageable 16 characters. This compression is vital when an engineer is literally parsing hundreds or thousands of these addresses to find the one single location where an error happened.
So low-level programming, network protocols, security research.
Anything where you're dealing directly with the hardware or the raw data stream, you have to deal in hex. It's the bridge between machine efficiency and human comprehension.
Okay, so hex is the necessary translation layer. Binary is the language of the transistors. And hex is the shorthand we use to communicate quickly about those massive streams of ones and zeros.
But whether we're using binary or hex, we're still just dealing with patterns of bits. And up until now, we've only talked about positive values. We haven't yet addressed the hardest conceptual problem in early computer design.
How do you represent polarity?
Yeah. How does a machine that only knows on and off possibly deal with negative numbers?
It feels like we're about to move from simple positive representation to a very ingenious but tricky solution to the sign problem. Okay, this is the pivot point where the complexity really ramps up. We've established that a bit is a 0 or a 1. A byte is 8 of those bits. There is no built-in physical mechanism for a plus or a minus sign.
None at all.
So if the computer reads a specific pattern, let's say 100, 0, 0, 0, 0, how can the processor possibly know if that's a small positive number or a large negative number or something else?
And this is where we have to stop treating the bits as just pure magnitude and start imposing a much more complex interpretation framework on them. The key answer is that the computer doesn't know anything inherently. The interpretation is decided entirely by the data type the programmer assigns to that chunk of memory.
So when you create a variable for an integer, you have to decide.
You have to make a choice. Is that block of bits going to be unsigned, meaning it can only represent positive numbers and 0, or is it going to be signed, meaning it needs to be able to represent both positive and negative values?
Let's look at the unsigned scenario first, because that's the easy part.
Unsigned is very straightforward. All 8 bits are dedicated purely to magnitude. So 000000000 and 111111 is 255. You get this clean, continuous range of 256 positive values.
Which is ideal for things that can never be negative, right? Like a file size or a memory address or the intensity of a color pixel.
Exactly. But if we need to represent negative numbers, we have to borrow some of that range. We have to sacrifice some of that potential positive magnitude to create space for negative polarity.
And this is where the genius of 2's complement comes in.
This is the system that virtually every modern computer uses today. Before 2's complement, early computers experimented with things like sign magnitude, where the first bit was just a simple flag for plus or minus.
Like a switch, 0 for plus, 1 for minus.
Right. And there was also 1's complement. Both of those systems were mathematically cumbersome, and this is the killer. They often resulted in 2 different ways to represent 0.
2 zeros. A positive 0 and a negative 0. That sounds like a recipe for constant bugs.
It was an absolute efficiency killer for the circuitry. 2's complement is so elegant because it solved that 2 zeros problem. And critically, it allows the computer to perform addition and subtraction using the exact same hardware logic, regardless of the sign of the numbers. Subtraction becomes simply adding a negative number.
Okay, so how does this ingenious trick actually work? Conceptually, what do we need to understand?
We need to understand that in 2's complement, the leftmost bit takes on a dual function. It's both a sign indicator and a weighted value.
So it's not just a flag anymore.
Not at all. In an 8-bit system using 2's complement, if that leftmost bit is a 0, the number is positive. If it's a 1, the number is negative. But that sign bit isn't just a flag. It actually represents a negative positional weight.
A negative weight.
Yes. In an 8-bit system, that leftmost position, which would normally be worth 2 to the 7th, or positive 128,
right,
it becomes minus 128.
Yeah. Minus 128. Wow, okay, that completely alters the calculation. So the positive range now only goes from 00000000000, which is 0, up to 0111111.
Right. And if you sum up the bits in 0, 1, 1, 1, 11, that's 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, you get the maximum positive value of plus 127.
And notice the immediate shift there. We sacrificed half of our positive range. We went from a max of 255 down to 127.
We did. We gave up those 128 positive values to gain the negative range from -1 all the way down to minus 128. The total number of available bit patterns is still 256, but now the range spans from -128 to plus 127.
Okay, that's the foundation. But to really get it, I think we need to walk through the actual calculation. How do you take a positive number and mathematically flip it into its negative equivalent? Let's use the decimal number -5.
Great example. So first we start with positive 5 in 8 bits. That's pretty simple. 000000011. That's a 4 and a 1.
Okay, step 1.
Step 1 is to invert the bits. This is also called taking the 1's complement. Every 0 becomes a 1 and every 1 becomes a 0. So 0000001 becomes 1111110.
Right. That string, 1111110, looks like a huge positive number, but that's not the final answer for Mega5, is it?
No. Step 2 is you simply add 1 to that inverted result. So 1011110 plus 1 equals 1011011.
So the binary pattern 111111 is how the computer stores the value -5.
That's it. And if we want to prove that it works, we can go backwards. We should be able to add our representation of +5, which was 000000101, to our new representation of -5, 1111111, and get 0.
Okay, let's do the addition. 0000000000001 plus 5 plus 1111111000000000.
That result is 9 bits long.
Oh, right.
Since we are operating in an 8-bit system, the processor simply discards that 9th bit, the overflow bit. It just falls off the end. And what we're left with is 000000000.
Which is 0. The system works perfectly, and it only used addition. It didn't need any special complex logic for subtraction or to check for signs separately. That is the definition of elegant engineering.
It's the ultimate proof of the concept that subtraction is just adding a cleverly disguised negative number.
And this brings us right to that critical aha moment. The one that highlights this whole problem of interpretation using that bit pattern we keep mentioning, 1111111. This one pattern represents two completely different numbers depending on the type the programmer declared.
Right. As we said, if a system is told to interpret that pattern as unsigned, 101111111 is the sum of all the powers of 2 up to 128. It's the absolute maximum value, 255.
But if the system is told to interpret that exact same pattern as a signed number using 2's complement,
the second it sees that leftmost one, it knows the number is negative. And if it were to calculate the 2's complement of 11111111 to find its positive equivalent, you'd invert it to 000000000, add 1, which gives you 1. Therefore, 1111111 must represent magus 1.
I need to pause on that because that is astonishing. The exact same pattern of switches all later on that represents the largest possible positive magnitude in one context, 255, represents the smallest negative magnitude, magus 1, in another.
Same physical reality. But the software, or a hardware instruction, tells the processing unit, treat this first bit as a sign, or don't. And that context, that single instruction, changes the meaning of the data entirely.
And if the programmer makes the wrong choice, or if data gets passed between two systems that assume different types, you have a critical failure waiting to happen.
Absolutely. Understanding 2's complement isn't just about knowing the range. It's understanding that negative numbers are represented by a mathematical trick, a trick that makes the hardware incredibly efficient, but also highly dependent on correct human declaration.
And that context dependency has massive real-life consequences. It goes way beyond simple arithmetic. It affects security, stability, even large-scale system performance. Let's delve into those consequences now. This is where the theoretical meets the, well, sometimes catastrophic. Okay, so this is the section where all the theory we just discussed, signed versus unsigned, 2's complement, range limits. This is where it translates directly into bugs, system failures, and real-world security vulnerabilities.
Because it's a design decision, not a hardware given. And if a system is designed poorly or makes a bad assumption, the misinterpretation can be profound.
Let's go back to an example like a temperature control system. Say it's monitoring a cooling line in some industrial plant. That temperature should absolutely be a signed number, right? Because it can obviously drop below 0.
Of course. But just imagine a scenario where this big industrial control system uses an older software library, or have a section of code written in C where the variable defaults to an unsigned integer. So the system is expecting a range from 0 to 255 degrees Celsius.
So what happens if the cooling line fails and the temperature rapidly drops to, say, -10 degrees? What does the computer try to store in that variable?
Well, the bit pattern for -10 and 2's complement is going to have the leftmost bit set to 1. The pattern is 101, 111, 1, and 10. Now, the unsigned system, it looks at 101, 110, 110, and it completely ignores the idea of a negative positional weight.
It just sees a big positive number.
It just sees 128 plus 64 plus 32 plus 16 plus 4 plus 2, which all adds up to 246.
So the system, which is dangerously freezing at -10 degrees, suddenly interprets the data as being dangerously hot at 246 degrees. The entire logic of the machine has failed because the interpretation was just wrong.
And the software might react by, shutting down the cooling pumps or triggering a high-temperature alarm. The physical system is frozen solid, but its digital twin believes it's overheating. This kind of logical failure is so common when data types are mismatched across API boundaries, or when old legacy code interacts with modern libraries.
And this leads us directly to the most famous consequence of these range limits, the concept of wraparound or integer overflow.
Wraparound is maybe the simplest concept here, but it's also one of those dangerous. It happens when an arithmetic operation produces a value that's bigger than the maximum capacity of the bits allocated for it. And instead of stopping, the value just wraps back around to the minimum value in its range.
Let's use the unsigned 8-bit example first. Max value is 255.
If your program tries to add 1 to an unsigned variable that's already holding 255, which is 1111111, the arithmetic logic unit in the processor tries to calculate 256. But 256 requires 9 bits to store. We only have 8 available.
So what happens to that 9th bit?
The 9th bit, the one carrying the value 256, is just discarded. It overflows. What's left behind are the 8 zeros.
000000000.
So the value jumps instantly from 255 all the way back down to 0. A counter suddenly resets. An index into a list suddenly points to the very beginning of the list when it should be pointing to nowhere.
It's a common and very frustrating source of minor bugs and off-by-one errors. But the wraparound effect is far more severe and frankly dangerous when you consider signed numbers, which in our 8-bit example range from -128 to +127.
So if a signed variable is sitting at its maximum positive value, +127, which is 0111111,
and you add just 1 to it, the arithmetic unit flips that leftmost bit to a 1, resulting in the pattern 100,000.
and since 102's complement is the largest negative number possible in that range, well, negative is 128, the value instantly jumps from +127 to -128. That is a radical, instantaneous, uncontrolled sign change.
I remember reading about a famous gaming bug where a resource counter, it was meant to track how many items a player could carry, it overflowed. The player tried to pick up one more item than the limit, which was 32,767.
The max of a 16-bit signed integer.
Right, and suddenly the counter flipped to -32,768, and the game treated them as though they had this massive deficit of items.
That's a perfect and thankfully harmless illustration of what can be a very severe vulnerability. In critical systems, these jumps can be exploited. Imagine a program uses a signed integer to check the length of some data a user provides, like a network packet. It's expecting that length to be a positive number.
Right.
But if an attacker can manipulate the input so that the length variable overflows, it goes past +127 and instantly wraps around to -128.
All the security checks in the program suddenly see a massive negative length.
And since a negative number is usually considered smaller than 0, the security logic that says, is the length of this data greater than 10,000, might suddenly pass, because -128 is of course smaller than 10,000.
The code misinterprets the negative value as an indicator of safe, minimal data.
When in reality, the data buffer is about to be overflowed with malicious code. It's a classic integer overflow vulnerability. The attacker uses the numerical limitations of the integer type itself to bypass security checks that are designed to protect the computer's memory.
So this isn't just a theoretical issue.
Not at all. This class of vulnerability is routinely found and exploited in critical infrastructure, in operating systems, in network components. The choice between signed and unsigned and the constraints of that range is a critical design decision that literally defines the security landscape for that piece of software.
So we've covered whole numbers, integers, and the critical problem of the sign, but the real world is full of numbers with decimal points. 3.14.005, your bank balance. How does the computer handle those non-integer values when it only speaks in powers of 2?
Yeah, that brings us to our final and maybe trickiest concept. The compromise we all have to accept.
The cost of representing the infinite. Okay, we've established that binary is a positional system based on powers of 2. You have the ones place, the twos place, the fours place, and so on. But fractional numbers, or numbers with decimals, they force us to think in terms of negative powers of 2.
Exactly. 2 to the power of -1, which is 1/2 or 0.5. 2 to the power of -2, which is 1/4, 0.5. 2 to the power of -3 is 1/8, 0.125, and so on.
So when you try to represent a number like 3.14 or even something as simple as 1/10, 0.1, you have to figure out how to combine those negative powers of 2 to hit that target decimal value.
But here's the kicker.
Yeah.
Often, you can't hit it exactly.
This is the decimal dilemma. So to handle these non-integer values, computers use what is called floating point representation. And the standard that's most commonly used across the globe is the IEEE 754 standard.
And that standardization is a really crucial historical point. Before IE 754, every major computer vendor implemented floating point math differently.
So you could run the same calculation on 2 different machines and get different answers.
You might get a slightly different answer. If you ran a complex scientific simulation on an IBM machine, you might get a slightly different result than on a DEC machine because their internal rules for rounding and precision were different. It was chaos for cross-platform scientific computing.
So the IE 754 standard, which was adopted back in the 1980s, effectively said, look, we all have to agree on one universal way to store and calculate these numbers, even if it means we have to agree on one universal imperfect way.
Precisely. It brought necessary uniformity. Now, when I hear the term floating point, what does that floating part actually refer to?
The floating refers to the location of the decimal point, or, in binary, it's called the binary point. Unlike integers, where we assume the point is fixed at the very end of the number, floating point is designed to maximize the range of numbers we can represent by allowing that binary point to move or float relative to the digits.
This is structurally very similar to scientific notation, which we use in human math all the time. Think of writing a huge number like Avogadro's number. 6.02 times 10 to the 23rd.
Okay, yeah. That number has a few key components. You have the significant digits, the 6.02, which tells you the precision of the measurement.
Right, and then you have the power of 10, the 10 to the 23rd, which tells you the scale or the range, tells you how big or small the number is. Floating point works the exact same way, just using bits allocated to 3 specific parts.
What are those parts?
In either a 32-bit or a 64-bit format, you have, first, the sign bit. Just a single bit, 0 for positive, 1 for negative.
Simple.
Then you have the exponent. This is a block of bits that determines the scaling factor. It effectively tells you where that binary point floats to, and this gives the number its huge range.
And the last part.
That's the mantissa, sometimes called a significant. This is the largest block of the remaining bits, and it stores the actual digits of the number. This is what determines the precision we can achieve.
So if the mantissa is long, we can be very precise. If the exponent is large, we can represent a huge number, like the distance to a galaxy. It's a really powerful compromise designed to handle vast scales.
It is powerful, but it leads us right back to the inherent flaw that our sources highlighted. Floating point is not perfect. Many simple, everyday decimals cannot be represented exactly in binary because we're using a finite number of bits.
And that's the most crucial insight for anyone who relies on digital math for precision. We're using a fixed number of bits, say 52 bits for the mantissa, in a standard double precision float to try and represent numbers that, when you convert them to binary, repeat infinitely.
It's just like fractions in base 10. If you try to represent 1/3, you get 0.33333, and it just goes on forever. At some point, you have to cut it off, you have to truncate it, and that truncation introduces a tiny rounding error. We just accept that error.
So what's a number that's perfectly clean in base 10 that becomes a repeating fraction in base 2?
The most famous culprit is the simple decimal value 0.1, 1/10. In base 10, it's perfect. But when you try to represent 110 using only combinations of powers of 2, 12, 14, 18, 116, 132, and so on, you can never, ever achieve 0.1 exactly. It results in a binary sequence that repeats infinitely.
And because the computer only has a finite number of bits in its mantissa, it has to cut that infinite sequence off somewhere.
Exactly. So when the computer tries to store 0.1, what it actually stores is an approximation that is slightly more or slightly less than the true value of 0.1. It might be stored as something like 0.100000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 And this leads us to that infamous example that every programmer learns the hard way, usually through a lot of frustration. Let's look at the simple arithmetic, 0.1 plus 0.2. In human math, the answer is exactly 0.3, no question. But when you ask a modern computer using standard IE 754 floating point math to do that calculation, the result you get back is 0.30000000000000004.
That tiny residual 4 appears way out at the 16th decimal place. Why is it there?
It's there because the computer didn't store 0.1 exactly and it didn't store 0.2 exactly. Both of them were slightly imperfect approximations because of that binary truncation. When you add those two slightly imperfect numbers together, those minute errors accumulate, and that accumulated error becomes visible in the final result.
So the computer isn't being dumb or failing to calculate correctly?
Not at all.
It correctly added two numbers that were already slightly wrong because of the necessary compromise of the binary system.
It is the unavoidable cost of representing infinite decimals with finite bits. That's it. It's a fundamental mathematical limitation of computing in base 2. You can increase the precision, you can use 64-bit double precision, but the problem never fully goes away. You just push the error further down the decimal line.
I remember a story about a famous bug in a popular spreadsheet program years ago where certain large calculations involving repeated addition of these tiny floating point numbers yielded a visible, incorrect result, all because of this cumulative error.
It happens constantly in scientific simulation, in weather modeling, in finance. And this is why if you were writing code for financial transactions where exactness is absolutely paramount down to the last cent, you never, ever, ever use standard floating point numbers to represent currency.
You have to use specialized decimal libraries or scale up the currency, right?
Absolutely. The standard practice is you store all dollar amounts as integers representing cents. So $5 is stored as 500, 30 cents is stored as 30. You perform all your arithmetic using robust, precise integer math, and only when you display the final result to the user do you convert it back to a decimal format.
That completely bypasses the inherent imprecision of floating point.
It avoids the problem entirely. It puts a really powerful practical spin on that theoretical limitation. Floating point gives us the massive range to model the entire universe, but we trade absolute precision for that range, and that trade-off has to be managed by the programmer.
And understanding why that error exists, that it's fundamental to the base 2 nature of computation and not just some software bug that is essential for truly mastering any kind of numerical programming.
Absolutely.
That brings us to the close of our exploration of digital numbers. Wow. That was a really thorough journey, deep beneath the surface of how our digital world handles the abstract concept of quantity. We went from simple on-off switches to the complex trade-offs of decimal representation. Let's try and synthesize the crucial knowledge nuggets we extracted.
I think the overarching synthesis is crystal clear. Numbers in computing are entirely interpretations of bit patterns. The pattern is a physical state, but the meaning, whether that pattern means 255 or maybe a 1, a whole number, or a fraction, that is determined by the context that we, the humans, impose on it.
Our journey began with binary, the native language of the computer, built on those positional weights of powers of 2, 1, 2, 4, 8, all, dictated by the simple necessity of transistor technology.
Then we introduce hexadecimal, which is that vital, human-friendly shortcut. Because one hex digit perfectly encodes 4 bits, it allows us to read, manage, and debug massive streams of data.
From memory addresses to color codes.
With an efficiency that binary just doesn't allow for humans.
Then we tackled that critical decision point, signed versus unsigned. This is where interpretation dictates the range and the polarity of a value. We saw the mathematical elegance of 2's complement and how that one pattern, 11, 1, 1, 1, 11, can mean 255 or NECA 1, depending entirely on the declaration of the data type.
And that context mismatch is responsible for some major software vulnerability. And finally, we discussed the complexity of floating point representation, standardized by AEC 744. It handles decimals, but forces us to accept that unavoidable compromise, that fractions like 0.1 cannot be represented exactly in binary.
Which leads to those tiny accumulated rounding errors that developers have to manage proactively, particularly in fields like finance that require absolute exactness.
It really is amazing how much clever engineering is packed into translating basic counting principles into a robust digital reality.
For you, the learner, understanding these underlying structures is just so essential. It's the difference between seeing a system fail and knowing why it failed. Often it's not bad code, but a fundamental mismatch of interpretation.
Agreed. And now that we understand how those physical bits are organized to represent abstract numbers, we have the perfect foundation for the next fundamental question of computing. We know what the patterns are. The next question is, how are those patterns processed?
How does the computer actually perform addition or comparison or storage using just these zeros and ones?
And that leads directly to the core building blocks of all computation. The final provocative thought we want to leave you with is this. The next logical step beyond numerical representation is to understand how those bit patterns become actionable instructions. This requires understanding the fundamental components that manipulate those patterns at the lowest possible level. The logic gates, N and D, or not T.
Which process these ones and zeros not as numbers, but as conditions for turning other switches on or off.
Exactly. And that is where the magic of digital calculation truly begins.